The edge of a black hole is a line you cannot cross and never come back. It marks the point where light itself gives up. The event horizon is defined as the surface where the escape speed equals the speed of light. Anything that reaches that surface, even a photon, cannot climb back out. It is not a material wall, just a limit set by the geometry of spacetime. On Earth, the escape speed is about 11 kilometers per second. The Sun's is roughly 600 kilometers per second. Near a stellar mass black hole, the required speed climbs to 300,000 kilometers per second, the very speed of light. The difference feels like stepping from a gentle hill into a sheer cliff. To picture the effect, imagine a stretched rubber sheet representing space. A massive object makes a dent. The deeper the dent, the steeper the slope. A black hole creates a funnel that drops straight down, and the rim of that funnel is the horizon. A marble rolled toward the edge slows, then disappears over the lip, never to return. Astronomers first inferred black holes from X-ray sources in the 1960s, where matter spiraled inward and heated to extreme temperatures. Later, radio observations of the center of our galaxy revealed a compact mass 10 million times that of the Sun, matching the predictions for a supermassive horizon. The recent image of a shadowed silhouette confirmed that something invisible blocks light at a precise radius. The horizon acts as a boundary for information, because any signal emitted inside must travel slower than light to escape, which is impossible. That means the state of matter that falls in cannot be communicated outward. In a sense, the universe loses access to that data the moment the surface is crossed. I find it hard to picture how a surface can hide everything yet be completely smooth. The mathematics tells us the curvature becomes infinite at the singular core, but the horizon itself remains a finite, well-behaved sphere. We don't really know what the interior looks like, only that it is cut off from the rest of the cosmos. Crossing the horizon also changes how time is measured. To an outside observer, an object appears to freeze as it approaches, its clock slowing to a crawl. To the traveler, proper time continues normally, and the horizon passes without a noticeable jolt. That duality is a direct consequence of the horizon's role in separating causally connected regions. One small detail that never ceases to surprise me is the way a photon hovering just above the horizon seems to linger, its frequency stretched into the red until it fades from view. It is a quiet reminder that the edge is not a sudden wall, but a gradual thinning of the light we can ever catch. Einstein's field equations tell us that mass tells spacetime how to bend, and that bend tells mass how to move. When a star collapses past a certain density, the curvature becomes so extreme that even light cannot climb out. The mathematics that describes that point is what we call a black hole. The simplest description comes from the Schwarzschild solution, a formula written in 1916 that assumes the object has no spin and no electric charge. It gives a radius, often called the event horizon, where the escape velocity equals the speed of light. For a black hole a few times the mass of our Sun, that radius is only about 9 kilometers. It is hard to picture a sphere that's small holding a mass that would normally fill a star many times larger. Yet the equations say the geometry inside that sphere is not empty space. It is a region where the metric coefficients flip sign and the roles of space and time swap. If you add rotation, the picture changes. The Kerr solution, derived in 1963, inserts an angular momentum term. The horizon becomes oblate and a new surface, the ergosphere, appears just outside it. In the ergosphere, spacetime is dragged around like a river pulling a leaf. Anything that tries to stay still is forced to co-rotate. The equations predict that energy can be extracted from this rotation, a process known as superradiance. The mathematics is clean, but the physical intuition feels slippery. Time itself stretches near the horizon. A clock held just outside the Schwarzschild radius ticks slower compared with a distant observer's clock. The factor is given by the square root of 1 minus the Schwarzschild radius over the radial coordinate. As you approach the horizon, that factor heads toward 0, so the distant observer sees your clock freeze. From the falling person's point of view, however, nothing special happens at the horizon. The proper time continues smoothly. I find it hard to picture two completely different experiences of the same event, yet the equations force that duality. The size of a black hole can be compared to familiar objects to keep the numbers in perspective. A black hole with 10 solar masses has a horizon roughly the size of a city block. A supermassive black hole of 1 billion solar masses stretches across the orbit of Mercury. The curvature at the horizon of the larger hole is actually weaker than that at the surface of Earth. That contrast reminds me that the equations care about mass density and the geometry, not about how big something feels. All of this rests on the assumption that Einstein's classical theory holds all the way down to the singularity. Inside the horizon, the Schwarzschild metric predicts that the radial coordinate becomes timelike, and the singularity sits at a finite proper time in the future of any infalling worldline. The curvature invariants diverge there. The math tells us the field equations break down. We simply cannot trust the solution beyond that point. It doesn't quite make sense when you say it aloud, a theory that predicts its own failure. Quantum considerations hint that the picture may be incomplete. Hawking's calculation shows that black holes radiate, losing mass over unimaginable spans of time. The radiation arises from quantum fields on a curved background, yet the background itself is supplied by classical general relativity. The interplay suggests that a full description must merge the two frameworks. Until we have a quantum theory of gravity, the interior remains a place where our equations hand us a singularity and then fall silent. Even within the classical domain, the equations set limits on what we can expect. The no-hair theorem tells us that, aside from mass, spin, and charge, all other details of the collapsing star are erased from the exterior geometry. The interior, however, could retain information in ways the metric does not capture. We don't really know whether the singularity is a point, a ring, or something else entirely. In the Kerr case, the singularity is a ring of 0 thickness, but the equations also admit closed time-like curves in its vicinity, paths that loop back on themselves. Whether such curves could exist in a physical universe is an open question. When we write down the field equations, we are balancing a geometric tensor against a stress-energy tensor. In vacuum, outside any matter, the right-hand side vanishes, leaving the Einstein tensor equal to 0. Solving that set of 10 coupled differential equations under symmetry assumptions yields the Schwarzschild and Kerr metrics. The elegance of the derivation is a reminder of how much can be extracted from a few simple premises. Yet the moment we insert matter at extreme densities, the stress-energy tensor becomes uncertain, and the solutions become speculative. The concept of time dilation near the horizon also has practical consequences for any hypothetical probe. If a spacecraft could hover just above the horizon using immense thrust, its onboard clocks would run far slower than those on Earth. A minute for the crew could correspond to years elsewhere. The equations give us the factor, but the engineering of such thrust is beyond current capability. It feels like a thought experiment that stretches the imagination without breaking the math. One more detail that often slips by: the gravitational redshift of light escaping from near the horizon. Photons climbing out lose energy, shifting toward longer wavelengths. The redshift factor mirrors the time dilation factor. The two are two sides of the same coin. If you were to watch a flash of light emitted just outside the horizon, it would appear stretched and dimmed, eventually fading into the background. The equations predict that precisely, even though we have never observed a flash from that distance. In the end, Einstein's equations give us a framework that is both powerful and fragile. They describe how spacetime bends around mass, they predict horizons, they tell us how clocks behave, and they expose a singular point where the math ceases to be meaningful. The limitations are as instructive as the successes, because they mark the borders where new physics must appear. I sometimes stare at a diagram of a Kerr black hole, the concentric circles of horizon and ergosphere, and I notice how the inner edge of the ergosphere almost kisses the horizon at the poles, leaving a tiny gap. That narrow space, where frame dragging is strongest, is a reminder that even in a solution we think we understand, geometry can hide subtle features that we are only beginning to sense. The idea that a black hole could leak anything at all feels almost absurd. Yet in the mid-1970s, Stephen Hawking took the equations of quantum fields and curved spacetime, nudged them together, and found a faint glow where none should exist. The glow is not a reflection of distant starlight. It is a steady stream of particles that seem to crawl out from the edge of the hole itself. To see how this happens, picture the horizon as a thin membrane of cold, empty space. Quantum theory tells us that even empty space shivers with pairs of particles and antiparticles that pop into existence for a fleeting instant. These pairs are born everywhere, but at the horizon the geometry stretches them apart. One member may fall in, the other escapes to the universe. The escaping particle carries away a tiny amount of energy, and the whole loses a corresponding bite of its mass. It is tempting to think of the process as a gentle leak, but the math shows it is more like a steady hiss of radiation. The temperature of that hiss is inversely proportional to the black hole's mass. A stellar mass black hole radiates at a few nanokelvin, far colder than the cosmic microwave background. A tiny black hole, if one ever formed, would blaze hotter, shedding mass faster, eventually evaporating entirely. When Hawking wrote down the spectrum of this emission, he recognized a familiar pattern. It matches that of a black body, the same curve that describes the glow of a hot piece of metal. That observation linked the horizon to thermodynamics. In the 1970s, Jacob B. Kenstein had already suggested that a black hole should have an entropy proportional to the area of its horizon. Hawking's calculation gave that entropy a concrete temperature, cementing the idea that black holes obey the same laws that govern steam engines. The temperature and entropy together raise a question that has haunted physicists ever since. If a black hole radiates away its mass, what happens to the information encoded in whatever fell in? In ordinary physics, the quantum state of a system evolves in a reversible way. You can, in principle, run the equations backward and recover the initial conditions. Hawking's original picture suggested that the radiation is completely thermal, carrying no imprint of the interior. Once the hole evaporates, the information would be gone forever, a violation of quantum unitarity. That tension is called the information paradox. It is not just a philosophical puzzle. It strikes at the heart of how we understand entropy, probability, and the very fabric of reality. If information can truly be destroyed, the statistical underpinnings of thermodynamics would need a rewrite. If it is preserved, then the radiation must hide subtle correlations that our simple thermal picture overlooks. Various proposals have tried to bridge the gap. Some argue that the Hawking particles are not truly independent. Instead, they are entangled with each other in a way that gradually releases the hidden data. Others suggest that the horizon is not a smooth surface, but a seething tangle of microscopic degrees of freedom, a fuzzball that radiates information directly. Still, another line of thought posits that the interior and exterior are linked by a worm-like bridge, allowing information to escape without violating locality. Each of these ideas reshapes the notion of entropy at the edge of a black hole, but none has yet achieved universal acceptance. Experimental verification remains a stubborn obstacle. The radiation from an astrophysical black hole is far too faint to detect against the background of cosmic photons. Laboratory analogs have therefore become the main avenue for testing the concept. In a fluid flowing faster than the speed of sound, a sonic horizon forms, mimicking the causal barrier of a black hole. Researchers have measured faint phonon emission that resembles Hawking radiation, though the connection to the true gravitational case is still debated. Similar analogs using Bose-Einstein condensates, optical fibers, and even superconducting circuits have reported signals that could be interpreted as analog Hawking photons. I find it hard to picture a lab table replicating the curvature of spacetime, yet the mathematics of the analog systems is strikingly similar. The same Bogoliubov transformations that turn vacuum fluctuations into real particles appear in both settings. When the experiments report a temperature that matches the predicted Hawking value, it feels like a small triumph, a hint that the underlying mechanism may be robust. The difficulty, however, is that analog experiments cannot capture the full information content of a genuine black hole. They produce thermal spectra, but they do not address whether the emitted quanta retain any imprint of what fell in. In that sense, the paradox remains untouched. Some groups are now looking for subtle correlations in the analog radiation, hoping to catch a glimpse of hidden structure. So far, the data are noisy, and the statistical significance is marginal. It doesn't quite make sense when you say it aloud. We might be seeing the same paradox in a lab, but we can't be sure. Beyond the lab, astrophysicists have searched for indirect signs of black hole evaporation. Primordial black holes, if they formed in the early universe, could be small enough today to be evaporating at a measurable rate. Their final burst would release a burst of high-energy gamma rays. Observatories such as Fermi have placed limits on how many such events could occur, but no definitive detection has emerged. The absence of evidence does not prove the absence of Hawking radiation. It merely tells us that any evaporation must be exceedingly rare or faint. Even without a direct measurement, the theoretical framework forces us to rethink entropy. If a black hole's entropy is proportional to its surface area, then the number of possible internal states scales with the area, not the volume. That insight inspired the holographic principle, which suggests that all the information in a region of space can be encoded on its boundary. The principle has become a cornerstone of modern attempts to unite gravity with quantum mechanics, even though its origin lies in the simple observation of Hawking's temperature. I often stare at the equations on a chalkboard and wonder whether the mathematics is telling a story or simply a bookkeeping trick. The paradox forces us to choose. Either accept that quantum mechanics is incomplete in the presence of strong gravity, or admit that our picture of spacetime needs a radical overhaul. Neither choice is comfortable, and both leave gaps that current theories have not yet filled. One experimental avenue that has gained attention is the use of ultra-cold atoms arranged in a lattice that mimics a curved metric. By tuning the interactions, researchers can create an effective horizon and watch particles appear out of the vacuum. The detection schemes rely on measuring tiny fluctuations in atom number, a whisper of a signal amid thermal noise. When a spike appears, it is tempting to label it Hawking radiation, but the community remains cautious, reminding us that alternative explanations always exist. The paradox also raises a practical question about the fate of information that falls into a massive black hole at the center of a galaxy. If the information is truly lost, then the galaxy's history would be partially erased each time a star is swallowed. If it is preserved in the outgoing radiation, then the universe carries a subtle record of every consumed object, encoded in a diffuse, nearly impossible to decode background. The notion that the universe could be a vast archive of such whispers is both awe-inspiring and unsettling. In the end, the picture is incomplete. The equations predict a temperature, an entropy, a slow bleed of mass, and a paradox that refuses to dissolve. Experiments push the boundary, but they cannot yet tell us whether the radiation is truly thermal or secretly structured. Theoretical work offers elegant possibilities, yet none have been proven. We sit with a half-filled cup, feeling the cold metal of the rim, aware that the liquid inside may be something entirely different from what the label says. A final note. The most recent analog experiment I read reported a minute shift in the frequency of emitted phonons, a deviation of just a few parts per million from the expected thermal value. It was enough to make the researchers pause, adjust their models, and wonder whether that tiny offset could be the first hint of hidden correlations. The lab was quiet, the detectors humming, and the data points lay on the screen like grains of sand waiting for a pattern to emerge. The idea that a black hole could hide a shortcut through space-time feels almost like a lab note written in the dark. Einstein-Rosen first put the notion on paper, describing a bridge linking two separate regions. I find it hard to picture a sheet of fabric stretched, then pinched, and suddenly a tunnel appears. The mathematics is tidy, two Schwarzschild solutions sewn together at a throat. That throat in the original model collapses instantly. It is a non-traversable wormhole, a fleeting passage that closes before anything could cross. The equations demand that any object trying to enter would be crushed by tidal forces long before the bridge even formed. In practice, the bridge is more a curiosity than a road. Physicists soon asked whether a different set of conditions could keep the throat open. The answer hinges on the energy conditions that general relativity normally imposes. Ordinary matter respects those rules, keeping curvature positive. To hold a tunnel open, you need something that pushes the opposite way, so-called exotic matter. Its pressure would be negative, effectively pulling space-time outward. We don't have a confirmed source of such matter. The Casimir effect shows that quantum fields can produce tiny negative pressures between metal plates, but scaling that up to astrophysical sizes seems far-fetched. I don't pretend to know whether the universe hides reservoirs of exotic energy. We simply lack the data. If a wormhole were stable, it would have to be traversable. That term carries a technical meaning. A traveler could enter one mouth, emerge elsewhere, and still have a chance to send a signal back. Traversable models often invoke a thin shell of exotic matter surrounding the throat, keeping it from pinching off. The shell would need to be incredibly thin, perhaps a few Planck lengths, yet strong enough to counter the black hole's gravity. Some proposals replace the exotic shell with a rotating, charged black hole, the Kerr-Newman solution. Rotation drags space-time around, creating an inner region where paths loop back on themselves. In theory, that could act as a gateway, but the interior is riddled with instabilities. Small perturbations grow quickly, turning any hopeful passage into chaos. I don't quite trust a picture that relies on perfect symmetry. The universe rarely offers that. Observationally, we have a handful of hints that could point to a hidden tunnel. One idea is that a wormhole mouth might mimic a black hole's shadow, but with subtle differences in the photon ring. High-resolution imaging of the event horizon could, in principle, reveal a bright spot where light leaks through the other side. So far, the images we have matched the expectations for a simple horizon, not a portal. Another proposed signature involves gravitational waves. If two wormhole mouths orbit each other, their merger would emit a waveform distinct from a black hole collision. The ringed-on phase might show echoes, repeated, weaker pulses, bouncing between the mouths. Recent data from detectors have shown tentative, low-amplitude echoes, but the statistical confidence remains low. We don't really know whether those patterns are noise or a glimpse of something exotic. Even if we found such a signal, interpreting it would be fraught with ambiguity. Many astrophysical processes can produce similar features. The temptation to label an oddity as a wormhole is strong, especially when popular fiction already paints them as shortcuts across the galaxy. Science fiction often shows a smooth tunnel with stars streaming by, a comforting visual that hides the harsh reality of extreme curvature and radiation. In the lab, we sometimes model wormholes using analog systems, fluid flows, optical fibers, or Bose-Einstein condensates. Those setups reproduce certain equations of motion, allowing us to watch effective horizons form and dissolve. They give us intuition, but they cannot confirm that a real astrophysical wormhole exists. The analogy stops at the mathematics. The underlying physics remains distinct. The debate over exotic matter also touches on quantum gravity. Some approaches, like loop quantum gravity, suggest that space-time has a discrete structure that could prevent singularities. If singularities are avoided, perhaps a bridge could survive the collapse. Yet those theories are still under development, and their predictions for wormholes differ widely. I find it hard to picture a lattice of space-time grains holding a macroscopic tunnel together without tearing. A final, more pragmatic point is that even if a wormhole existed, it might be too small to be useful. The throat could be on the order of a few kilometers, or even less, making any passage fatal to a human or spacecraft. The tidal forces near the mouths would stretch and compress any object beyond recognition. In that sense, the concept remains more of a theoretical curiosity than a practical root. Still, the very fact that Einstein's equations admit such solutions keeps the idea alive. It reminds us that the language of geometry can describe structures we have never observed. The mathematics does not demand that nature builds them, but it does not forbid them either, provided the right kind of energy is present. When I look at the latest X-ray spectra from a candidate black hole binary, I notice a faint, periodic dip in the high-energy tail. It could be a statistical fluctuation, or perhaps a subtle hint of photons escaping through an unseen opening. The pattern repeats every 0.73 seconds, just long enough to register on the detector, then disappears. It sits there, waiting for a better instrument to decide whether it is a whisper of a bridge or simply noise. I sit in the dim lab, the blackboard humming with equations, and think about black holes as possible doors. The idea feels heavy, like a cold stone pressed against my chest. One proposal suggests that during inflation the universe sprouted countless bubbles, each expanding in its own space. If a bubble collided with a collapsing star, the resulting black hole might connect the two regions. That picture gives a grainy sense of a tunnel, not a smooth passage. But the math behind eternal inflation is tangled, and we cannot watch a bubble grow. We simply write down probabilities and hope the numbers capture something real. Another line of thought comes from black hole complementarity, a principle that tries to keep information safe. Inside the horizon, an observer would see a wall of fire, while an outside watcher sees nothing. If both views are correct, perhaps the interior is a mirror that reflects another universe. The mirror idea feels like a cold glass. You can touch it but not see through. String theory adds a different flavor, offering a vast set of possible vacuum states. Each vacuum could correspond to a universe with its own laws, a patch in a larger picture. When a black hole forms, some argue it might tunnel into one of those patches. The tunnel would be tiny, perhaps the size of a Planck length, yet its effect could be huge. I find it hard to picture a Planck-sized doorway opening onto a whole universe. Our instruments cannot probe that scale, so the idea stays in equations and imagination. The biggest obstacle is that we lack a complete quantum theory of gravity. Without it, any bridge between black holes and other vacua is speculative at best. Some researchers suggest that the singularity is replaced by a bounce, a rebirth into another cosmos. A bounce would feel like a sudden pressure, a squeeze and release in spacetime. But calculations show the bounce may be unstable, collapsing back before any exit forms. We don't really know whether such a bounce could survive the intense tidal forces. Even if a tunnel exists, we have no clue how information would travel through it. Information might be scrambled beyond recognition, like static on an old radio. Or perhaps complementarity ensures that no single observer ever sees a violation of physics. That safety net feels comforting, yet it leaves the portal idea hanging in the dark. If black holes are windows, what would we see on the other side? Some speculate a universe with different constants, where chemistry runs on silicon instead of carbon. The notion gives a chill, like stepping into a room where the air smells unfamiliar. Yet we have no way to test such a claim, no signal to catch. Current challenges include reconciling Hawking radiation with any exit pathway. If radiation leaks out, the tunnel might close before anything passes. We can write down a model where the tunnel persists, but it feels like forcing a square peg. The peg is our intuition. The hole is a theory still being carved. At times, I wonder whether the whole picture is a mirage, a projection of our desire for escape. Even if the portal is real, it may be one way, a one-sided throat. A traveler could fall in, never to return, while the outside world remains unchanged. That asymmetry feels like a cold draft slipping through a cracked window. Perhaps the most honest statement we can make is that the question is still open. I hear the lab's ventilation humming, reminding me that even the simplest sounds travel through curved space. A faint vibration on the detector hints at motion, but we cannot tell if it is a murmur from elsewhere. The bubble universe picture suggests a multiverse that constantly sprouts, like foam on a cold beer. If a black hole sits at the junction of two bubbles, the interface could be turbulent. Turbulence would generate gravitational waves, ripples we might someday hear with better detectors. So far, the signals we have captured match mergers, not exotic tunnel signatures. That mismatch makes me uneasy, as if we are listening for a song with the wrong instrument. Black hole complementarity also raises the question of who gets to define reality inside. An infalling observer experiences a smooth fall, while an outside observer sees a frozen horizon. If both descriptions are valid, perhaps reality is observer-dependent, a patchwork rather than a single fabric. That notion shakes the idea of an objective universe, a point that unsettles many. String theory's framework paints a picture of 10,500 possible vacua, each a different set of laws. If black holes can sample that framework, they would act like random dice in a dark room. But dice need a surface to roll on, and we lack a clear definition of that surface. Current attempts use holographic dualities, mapping a black hole's interior to a lower dimensional field theory. The mapping works well for certain idealized black holes, but real astrophysical ones are messier. Messiness introduces unknown corrections that could destroy any neat portal picture. We also face the firewall paradox, which suggests a searing wall at the horizon. If a firewall exists, any traveler would be incinerated before reaching a possible exit. Some argue the firewall is an artifact of our calculations, not a physical reality. Without consensus, the portal hypothesis remains speculative, balanced on a fragile theoretical scaffold. Nevertheless, the idea pushes us to ask what it means for reality if space can split. If space can split, perhaps reality is more like a set of overlapping sheets than a solid block. That image feels tactile, like stacked cards you could slide apart with a soft push. A black hole might be the finger that lifts one card, exposing the one underneath. If so, the lifted card could reveal a universe with different particle families. We have no way to verify that, and the speculation can feel like chasing shadows. Still, the mathematics does not forbid such connections, and that alone keeps the question alive. Future observations of black hole shadows may reveal subtle deviations hinting at extra dimensions. The Event Horizon Telescope already gave us the first image, but resolution remains coarse. Improved arrays could someday capture fine structure, perhaps a faint outline of a tunnel. Until then, we work with thought experiments, sharpening equations like a whetstone on a blade. Each refinement feels like a small pressure, testing whether the idea will crack or hold. I often wonder whether the answer lies not in grand theories but in a quiet anomaly. A single photon that behaves oddly near a horizon could be the clue we need. Detecting such a photon demands instruments that can survive extreme gravity, a daunting engineering feat. Even if we build them, interpreting the data will be fraught with uncertainty. Uncertainty is the companion of any attempt to peer beyond an event horizon. Perhaps the most honest thing we can say is that the portal idea is a useful lens. It forces us to question what we call space, time, and the boundary between worlds. In the quiet of the lab, the hum of the cryostat reminds me of distant echoes. Those echoes might be the faintest hint that something else waits beyond the darkness. The equations that describe a black hole's exterior are tidy, almost comforting. Inside, they point toward a point where the numbers stop making sense. Mathematically, we write the metric as a smooth function of radius, then let the radius go to zero. At that limit, the curvature term shoots to infinity. Infinite curvature is not a number we can handle. It is a signal that the formula has reached its limit. I write infinity in the margin and pause. The same limit forces the density term, mass divided by volume, to blow up as well. A handful of solar masses squeezed into a volume smaller than a grain of sand would feel like a weight of a mountain pressed into a single point. General relativity tells us that mass tells spacetime how to curve, and curvature tells mass how to move. When curvature becomes infinite, the rule itself collapses. I have spent years trusting the Einstein field equations to predict planetary orbits, light bending, even the expansion of the universe. Now they hand me a singularity and refuse to go further. The breakdown is not just a mathematical curiosity, it means the theory cannot describe what actually happens there. We cannot say whether time continues, stops, or loops back on itself. One way to see the problem is to imagine dropping a clock toward the center. The clocks tick slow, then freeze at the horizon, and beyond that the equations give no answer. Another thought experiment replaces the clock with a thin sheet of paper. As the sheet approaches the core, its area shrinks without bound, yet the paper's material cannot vanish. These mental tricks highlight the same issue. The geometry ceases to be a smooth fabric. Instead, it becomes a knot with no threads left to follow. Physicists have tried to patch the hole with extra terms, hoping to tame the infinity. Adding a pressure term that resists collapse sounds reasonable, but the equations still drive the pressure to infinity. The failure is systematic. Any attempt that stays within classical general relativity hits the same wall. The wall is built from the very assumptions that gave us the theory's successes. To move beyond, we must bring quantum mechanics into the picture. Quantum theory teaches that fields cannot be localized to arbitrarily small regions without costing huge amounts of energy. If we treat spacetime itself as a quantum field, the notion of a point may dissolve. Instead of a single point of infinite density, we might get a fuzzy region where the concept of location loses meaning. Loop quantum gravity, for example, suggests that space is made of tiny loops, each with a minimum area. When the collapse reaches that scale, the loops could repel further compression. String theory offers a different picture. Fundamental strings cannot be squeezed below their own length. If the core is made of strings, the singularity could be replaced by a compact, highly excited state. Both approaches share a common hope: that the infinities are artifacts of using a classical description where a quantum one is required. I find it hard to picture a fuzzy core, because my intuition is trained on solid objects. Even if a quantum description removes the infinity, we still lack a clear picture of what time does there. Does time end, or does it branch into another direction we cannot yet label? Some researchers propose that the interior connects to another region of spacetime, a kind of bridge. The mathematics of such bridges, called wormholes, also runs into singularities unless exotic matter is introduced. Exotic matter with negative energy density has never been observed in the lab. So the bridge idea remains speculative, a useful illustration rather than a proven path. Another line of thought treats the singularity as a place where information is lost. If information truly disappears, it would violate a cornerstone of quantum theory. The information paradox has driven many of the recent debates, pushing theorists to look for mechanisms that preserve information. One proposal is that the horizon itself stores the data, leaking it back slowly as Hawking radiation. Yet Hawking radiation is derived from a semi-classical treatment that still assumes a smooth horizon. If the core is not smooth, the derivation may need revision. I sometimes write a short note in the margin. What if the core is a quantum foam constantly bubbling? The phrase quantum foam evokes a picture of tiny, ever-changing bubbles, but it is only an analogy. In practice, we have no experiment that can probe distances smaller than the Planck length, about 10⁻³ meters. All our data stops at the horizon, where light can still escape. Because of that observational barrier, the singularity remains a theoretical laboratory. We test ideas by checking whether they reproduce the known external behavior of black holes. If a quantum gravity model predicts the same orbit of a star around a black hole, we consider it viable, even if it says nothing concrete about the interior. This pragmatic stance keeps the field moving, but it also means we never directly verify what lies at the core. We are left with a collection of possible pictures, none of which can be confirmed. The thought experiments I mentioned earlier serve as sanity checks. If a model predicts that a sheet of paper can be compressed to zero area without infinite pressure, I raise an eyebrow. Such a result would clash with everyday experience of matter resisting compression. It would also suggest that the model has introduced new physics that we have not seen elsewhere. Conversely, if a model tells me that a particle's wave function spreads out infinitely as it approaches the core, I note the similarity to the curvature blow up. At least the model mirrors the known failure of classical theory. One recurring theme in these speculations is the idea of spacetime termination. Imagine a line of train tracks that simply stops. The train cannot go further, but the tracks themselves end abruptly. If spacetime truly ends, what happens to objects that reach that end? Do they cease to exist, or do they transform into something else we cannot describe? I find it hard to picture an end without a surrounding environment. Ends imply a boundary, but a boundary needs something on the other side to define it. Perhaps the boundary is not a spatial edge but a temporal one, a moment after which the notion of before loses meaning. In that case, the singularity would be more like a final tick of a clock that never ticks again. The idea of a final tick feels unsettling because it suggests a place where causality stops. Causality is the backbone of every experiment I have ever recorded. If causality fails, the whole edifice of physics would need a new foundation. That prospect is both terrifying and oddly exciting. Still, I keep reminding myself that all these pictures are built on equations that we know are incomplete. We have not yet written a single, self-consistent set of equations that merges gravity with quantum fields at all scales. Until such a theory arrives, the singularity remains a placeholder for unknown physics. It is a reminder that our current map has a blank spot. Sometimes, in the quiet of a late night, I stare at a simulation of a collapsing star. The pixels converge, darken, and then the program stops, unable to render anything beyond a certain point. That pause on the screen mirrors the pause in our understanding. It is a small, stubborn glitch that refuses to smooth over. The most concrete thing we can say is that the singularity forces the curvature scalar to diverge. Beyond that, we have no reliable measurement, no direct observation, only the echo of equations that scream infinite. I write down the scalar curvature, label it r right arrow infinity, and then draw a tiny circle around it as if to contain the chaos. The circle is a habit, not a solution. In the end, the core of a black hole is a place where our trusted tools, differential geometry, smooth manifolds, no longer apply. It is a reminder that nature can be harsher than any of our neat mathematical boxes. When I close the notebook, I notice a faint smear of ink where the word infinite meets the margin. The ink has bled slightly, leaving a tiny, uneven halo. The event horizon feels like a thin, cold membrane, its temperature barely above absolute zero. I record that any particle crossing it disappears from external view, yet something remains. The holographic principle claims that every bit of data inside the black hole lives on that membrane. It is a statement about information, not about mass or charge alone. I find it hard to picture how three-dimensional content could be stored on a two-dimensional surface. In the 1990s, a conjecture emerged linking a gravity theory in a curved space to a quantum field theory on its edge. That is the AD-SCFT correspondence, a precise mathematical bridge. It tells us that a bulk of spacetime can be fully described by a theory living on its boundary. The bulk here means the interior of the black hole, the boundary, the event horizon. If the correspondence holds, the horizon must encode every field configuration inside. I don't quite grasp how a single pixel could hold an entire galaxy's history. The encoding is not a simple copy, it is a highly compressed map. Quantum entanglement weaves together distant points, allowing information to be spread across the surface. When two particles become entangled, their joint state lives partly on the horizon, even if one falls inward. Entanglement entropy, a measure of that spread, matches the area of the horizon rather than its volume. That area law is the first clue that geometry and information are linked. It feels like a thermometer that reads temperature by the size of a wall, not the size of a room. Experimentalists have built analogs in condensed matter systems, where a thin layer mimics a horizon. In a cold atom lattice, edge modes carry the same information as bulk excitations. Those lab setups give us a tactile sense of a holographic mapping, though they are far from a real black hole. The correspondence suggests that space itself may be emergent, a collective effect of underlying bits. If three-dimensional reality is a projection, then distance is a derived quantity. I admit I can't yet translate that into a concrete picture of everyday space. One consequence is that the interior singularity might never be a physical point. Instead, the singular behavior could be an artifact of using the wrong description. When we switch to the surface language, the singularity disappears, replaced by smooth data on the horizon. This perspective also offers a way around the information paradox. If information never truly leaves the horizon, it can be recovered from the emitted radiation. The Hawking particles would carry encoded bits, like a faint echo of the interior. Calculations using the AD-SCFT framework show that the entropy of a black hole equals the number of quantum states on its boundary. That equality is not a coincidence. It is built into the mathematics. It does not answer how the encoding works, only that it must exist. Some models describe the horizon as a lattice of Planck-scale pixels, each holding a few bits. The total count matches the Bekenstein-Hawking entropy, the familiar area law. I sometimes wonder whether those pixels are like grains of sand, each indistinguishable until examined. Quantum error correction codes have been proposed as the language of this holographic storage. In such codes, the loss of a few surface bits does not destroy the bulk information. That resilience mirrors the way a black hole seems to preserve its content despite extreme conditions. Condensed matter experiments with topological insulators reveal edge currents that are immune to disorder. Those currents act like the horizon's information channels, robust against perturbations. Seeing that in a lab makes the abstract idea feel a little more tangible. The holographic view also reshapes our intuition about locality. 2 points deep inside the black hole may correspond to nearby patches on the horizon, or far apart ones. I don't quite know how to reconcile that with everyday notions of distance. If the interior is a projection, then probing it directly becomes a question of decoding the surface. Current techniques rely on scattering experiments and theoretical inversion, much like reconstructing an image from its shadow. The inversion is notoriously unstable, and we often end up with blurry pictures. The AD-SCFT correspondence is exact only for spacetimes with a negative cosmological constant. Our universe appears to have a small positive constant, so the direct application is uncertain. We don't really know whether the same holographic logic extends to our own cosmos. Nevertheless, many researchers treat the principle as a guiding heuristic. It forces us to treat geometry and quantum information on equal footing. That shift feels like moving from a wooden ruler to a digital sensor, more responsive, yet still measuring length. In practice, the principle has inspired new computational tools. Tensor networks, for example, mimic the hierarchical structure of a holographic map. Running those networks on a computer produces visualizations that resemble warped slices of spacetime. Those visualizations are not literal pictures of a black hole's interior, but they encode the same relationships. They help us see how a low-dimensional boundary can generate a higher-dimensional bulk. I sometimes stare at the output and feel the weight of the abstraction pressing against the screen. The idea that reality could be a projection raises philosophical questions about what we call real. If all observable phenomena emerge from surface data, then the bulk may be a convenient fiction. That notion unsettles me because it blurs the line between measurement and imagination. Yet, the mathematics does not lie. Equations derived from the holographic principle reproduce known thermodynamic properties of black holes. When the numbers match, I feel a brief, quiet confidence that something is right. Experimental analogs in superconductors have shown that vortex cores act like tiny horizons. Their edge modes carry information about the bulk condensate, echoing the black hole case. Those lab results are far from a full proof, but they keep the idea grounded. The principle also connects to recent work on quantum gravity's soft hair. Soft hair refers to low-energy excitations on the horizon that store information. If those excitations are the bits of the hologram, then the horizon is more textured than a smooth sheet. I sometimes write down the horizon's area in Planck units, then divide by 4 and watch the entropy emerge. It is a simple arithmetic step, yet it encodes an entire universe's worth of states. The simplicity is both comforting and bewildering. One lingering question is how time fits into the holographic picture. If space is a projection, does time also emerge from the surface dynamics? We lack a clear answer, and the silence of the equations feels heavy. In some approaches, the boundary theory includes a notion of time that maps onto bulk time. That mapping preserves causality, ensuring that cause precedes effect in both pictures. I find it hard to picture a clock on the horizon ticking for everything inside. The holographic principle forces us to rethink the meaning of inside and outside. Inside a black hole may simply be a different description of the same surface data. That inversion flips our intuition, like looking at a painting from behind. Even if the principle is only an approximation, it has already reshaped theoretical physics. It has guided the search for quantum gravity, informed string theory, and inspired new condensed matter models. Each of those applications feels like a small step toward a larger, still hidden structure. The principle's elegance lies in its economy. A two-dimensional sheet carries all the information of a three-dimensional volume. That economy reminds me of a compressed file that expands when opened. The compression algorithm, however, remains a mystery. When I write notes on the black hole horizon, I sometimes sketch a grid of tiny squares. Each square represents a Planck area pixel, a potential carrier of a few bits. The grid feels like a cold metal plate, each facet reflecting a faint, distant light. In the lab, we can cool a thin film to near absolute zero and watch edge currents flow. Those currents act as carriers of information, just as the horizon's pixels should. Seeing that parallel makes the abstract claim feel less like a metaphor and more like a physical process. The holographic principle does not claim that the universe is a literal movie screen. It suggests that the fundamental description may be lower dimensional, with our perception adding depth. That suggestion is both modest and daring, depending on where you stand. I sometimes wonder whether an advanced civilization could read the horizon's code directly. If they could, they might reconstruct the interior without ever crossing the boundary. We have no evidence of such technology, and the idea feels speculative at best. Nevertheless, the principle offers a concrete framework for testing ideas about quantum gravity. It gives us equations, boundary conditions, and predictions that we can, in principle, verify. Those predictions are subtle, often requiring indirect measurements. One promising direction involves measuring the entanglement spectrum of a condensed matter system. If the spectrum matches that predicted by a holographic dual, the correspondence gains empirical support. So far, the data are suggestive but not definitive. The principle also implies that black hole evaporation does not destroy information. Instead, the information leaks out encoded in subtle correlations among the Hawking quanta. Detecting those correlations is a technical nightmare, far beyond current instruments. In the end, the holographic principle remains a hypothesis anchored by mathematical consistency and occasional experimental hints. It is a tool, not a final answer, guiding us through the darkness of the unknown. I keep a notebook of the equations, the doubts, and the tiny observations that keep the work alive. Tonight, as the lab lights dim, I glance at the monitor displaying a lattice of simulated horizon pixels. One pixel flickers, its intensity shifting by a fraction of a percent. That tiny change reminds me that even the smallest fluctuation on a surface can echo through an entire volume. I sit with the equations, the way one might stare at a weathered instrument panel, trying to hear what it will say about the heart of a black hole. Loop quantum gravity offers a picture of spacetime built from tiny, indivisible chunks, like a mosaic of Planck-scale tiles. The theory insists that area and volume cannot be divided indefinitely. They come in discrete steps. When I write the area operator for a horizon, the numbers jump, not flow. This granularity is meant to stop the infinite curvature that general relativity predicts at the singularity. In the loop picture, the collapse of a star squeezes the geometry until the quantum of area is reached. At that point, the equations suggest a bounce, a reversal of the inward pull. The interior then expands into a new region that some authors call a white hole. I find it hard to picture a spacetime that flips like a rubber sheet, yet the mathematics does not allow the curvature to diverge. The bounce is not a smooth curve. It is a sudden change in the eigenvalues of the volume operator. String theory takes a very different route. It replaces point particles with one-dimensional strings that vibrate in a space that carries extra dimensions beyond the three we experience. Those hidden dimensions are compactified, curled up at scales far below any detector. The string's tension sets a natural length, and when curvature grows to that scale, the notion of a point singularity dissolves. Instead of a point, the core of a black hole becomes a fuzz of strings and brains, sometimes called a fuzzball. The fuzzball picture claims that each microstate of the black hole is a distinct configuration of strings, filling the interior with structure. Both approaches claim to resolve the singularity, but they do so with different language. Loop quantum gravity speaks of a discrete geometry that forces a bounce. String theory speaks of a dense tangle of extended objects that replaces the point. I don't know which description is closer to reality. The calculations live in regimes we cannot yet test directly. The two frameworks also differ on what happens to information that falls in. In the loop scenario, the bounce may allow information to re-emerge through a white hole phase. In the fuzzball picture, information never disappears because each microstate is already encoded in the string configuration. Predictions for observable signatures are where the theories begin to meet the data. Gravitational wave detectors have opened a window onto the ringing of black holes after merger. If the interior is replaced by a discrete lattice, the ringing might include faint echoes, small repetitions of the main signal arriving milliseconds later. Those echoes would arise because the effective potential near the horizon is altered by the quantum geometry. I have seen a few tentative analyses that claim to find such patterns, but the statistical significance remains low. The string community points to similar echoes, but their origin is tied to the reflective surface of a fuzzball rather than a lattice bounce. Both explanations predict a deviation from the clean exponential decay expected from classical general relativity. Current research programs try to turn these speculative signatures into concrete numbers. Loop groups run numerical simulations that implement the polymer quantization of geometry on a lattice that mimics the interior. They compute the quasi-normal mode spectrum and look for shifts that could be measured. String theorists, on the other hand, construct explicit fuzzball solutions in simplified settings, often in 5 dimensions with supersymmetry, to extract the reflectivity of the surface. They then feed that reflectivity into black hole perturbation theory to predict echo amplitudes. Both camps are aware that the calculations are delicate. A small change in boundary conditions can erase the signal entirely. We don't really know how robust these predictions are when the full, messy astrophysical environment is added. The experimental side is equally tentative. Advanced LIGO and Virgo have accumulated dozens of merger events, each with a final ringed-on phase that could hide echoes. Analysts apply matched filter techniques, looking for a secondary pulse that repeats with a roughly constant delay. The delay length is tied to the distance between the would-be horizon and the reflective surface, which in turn depends on the quantum scale. Some groups report a few percent improvement in fit when an echo template is added. Others find no improvement at all. The community remains divided, and the debate feels like watching a slow-moving tide rather than a sudden wave. Beyond echoes, there are more subtle effects. Loop quantum gravity predicts that the entropy of a black hole is proportional to the number of punctures where spin networks intersect the horizon. That counting leads to a correction term that scales with the logarithm of the area. If such a correction were measurable in the spectrum of Hawking radiation, it could be a smoking gun. Yet Hawking radiation is far beyond our current detection capability. String theory offers a different correction. The presence of extra dimensions changes the relationship between mass and temperature for small black holes. In principle, a microscopic black hole created in a high-energy collider would evaporate differently if extra dimensions were accessible. No such events have been observed, and the energies required are still out of reach. Both programs maintain active collaborations across theory and experiment. Loop groups host workshops where mathematicians, physicists, and computer scientists exchange code for spin foam simulations. The string community convenes at conferences that blend formal string constructions with phenomenological models of black hole microstates. Funding agencies have begun to list quantum gravity as a priority area, encouraging cross-disciplinary proposals. I have watched grant proposals list both loop and string approaches side by side, hoping that competition will sharpen the predictions. It is a modest optimism, not a grand promise. There are points where the two frameworks intersect, even if only briefly. The holographic principle, originally born from string theory, suggests that the information content of a volume can be encoded on its boundary. Loop quantum gravity has a version of this idea in the way spin networks intersect a surface, assigning degrees of freedom to the punctures. This convergence hints that the two pictures might be different languages describing the same underlying structure. I find it hard to picture how a discrete network of areas could be equivalent to a smooth manifold wrapped in extra dimensions, yet the mathematics does not forbid such a duality. Nevertheless, each approach retains its own set of assumptions. Loop quantum gravity starts from the canonical quantization of general relativity, keeping the spacetime metric as the primary variable. String theory starts from a perturbative expansion of a world sheet action, treating gravity as an emergent phenomenon from a higher dimensional theory. The assumptions shape the predictions for what lies beyond the horizon. In the loop view, the interior is a quantum bounce. In the string view, it is a tangled web of strings. Both claim to avoid the infinite density that classical theory predicts, but they do not yet agree on the detailed physics of that avoidance. Experimental constraints may eventually tip the balance. If future detectors, such as the Einstein telescope or cosmic explorer, reach sensitivities that can resolve echo amplitudes an order of magnitude lower, the presence or absence of echoes could become decisive. Alternatively, a detection of a deviation in the black hole mass-spin relation that matches a string theoretic correction would lend weight to extra dimensions. Until then, the field lives on a thin line between mathematical elegance and empirical scarcity. I sometimes feel the weight of that uncertainty pressing against the page as I write. One concrete observation that keeps me grounded is the way the waveform's tail behaves in the latest simulated merger. The tail shows a slight, persistent wiggle at a frequency that matches the predicted spacing of loop area eigenvalues. It is a tiny feature, just a few parts in 10,000, but it persists across several runs. I have not yet been able to rule out a numerical artifact. The data sit there, quiet, waiting for a better instrument or a sharper theory to tell me whether that wiggle is a clue or a coincidence. The Event Horizon Telescope finally gave us something that looks like a silhouette, dark, round, surrounded by a thin ring of bright plasma. The image of M87 was not a photograph in the ordinary sense. It was a reconstruction from a global network of radio dishes, each recording a tiny fraction of the signal. When the data were combined, the ring's diameter matched the size predicted for a black hole of 4 billion solar masses, within a few percent. I find it hard to picture how a beam of radio waves stretched across the planet can resolve an object 100 million light-years away, yet the numbers hold up. A second image of our own galactic center arrived later. Sagittarius A** is smaller, its variability faster, the ring less steady. The EHT team had to sift through rapid changes in brightness, stitching together a picture that flickered like a candle in a draft. The resulting shadow still aligns with the Kerr metric, but the uncertainties are larger, leaving a sliver of room for alternatives. We don't really know whether the slight asymmetry in the ring is a sign of an exotic horizon structure or just turbulent plasma. Gravitational wave observatories have been listening to the universe in a very different way. Since 2015, LIGO and Virgo have recorded dozens of black hole mergers, each event a brief chirp that rises in frequency before the final plunge. The waveforms carry information about the masses and spins of the merging objects, and about the way spacetime rings down after the merger. When the signal decays, the frequencies match the predictions for a Kerr black hole's quasi-normal modes, no obvious deviations. Still, the signal-to-noise ratio is modest. Subtle departures could be hidden beneath the noise floor. I sometimes stare at a plot of the ringdown and wonder if a faint echo might be there, waiting for a detector that can hear it. X-ray telescopes have been probing the innermost regions of accretion disks for years. Instruments like XMM Newton and NuSTAR measure the iron K alpha line, which becomes broadened and skewed by extreme gravity. The line's red wing extends down to energies that suggest the inner edge of the disk lies just a few gravitational radii from the horizon. Radio interferometers such as the VLBA trace the base of relativistic jets, revealing a collimated outflow that seems anchored to the black hole's spin axis. The combination of X-ray spectroscopy and radio imaging gives a picture of a rotating spacetime that drags nearby matter along, consistent with frame dragging in general relativity. Polarization measurements add another layer. The Imaging Polarimetry Explorer, IXPE, has begun to map the orientation of X-ray photons emerging from the corona. A preferred polarization angle could indicate ordered magnetic fields threading the horizon, perhaps supporting models where the spin energy is extracted to power jets. The data are still noisy, and the interpretation hinges on assumptions about the geometry of the emitting region. I find it hard to picture the exact configuration of magnetic loops near the horizon. The models feel like sketches rather than precise blueprints. Future missions promise to tighten the constraints. The Laser Interferometer Space Antenna, LISA, will listen to lower-frequency gravitational waves, those emitted by massive black hole binaries spiraling together over months or years. By tracking the inspiral for a long time, LISA can measure the masses and spins with unprecedented precision, and it may even catch the subtle imprint of a non-Kerr multipole moment. If a black hole were replaced by a gravistar or a wormhole, the inspiral phase would deviate in a characteristic way. The mission is still years away, but the design papers already discuss how to translate a tiny phase shift into a test of exotic physics. The James Webb Space Telescope, though primarily an infrared observatory, can contribute indirectly. Its sensitivity to dust-enshrouded galactic nuclei will let us study the environments where black holes grow. By measuring the spectral energy distribution of active galactic nuclei, JWST can infer the accretion rate and the geometry of the surrounding torus. If the inflow of matter is more chaotic than we think, the inner disk might be warped, affecting the way the shadow appears in radio images. I sometimes wonder whether a misaligned disk could masquerade as a deviation from the Kerr solution. All these data streams, radio shadows, gravitational wave chirps, X-ray spectra, polarization angles, are being fed into a growing suite of statistical tools. Bayesian model comparison lets us ask whether a firewall, a fuzzball, or a simple Kerr black hole better explains the observations. So far, the simplest model wins, but the odds are not absolute. Small systematic uncertainties in the calibration of a detector or in the modeling of plasma physics can shift the balance. We don't really know how much of the remaining parameter space is truly open to exotic ideas and how much is just the margin of error. There are also attempts to look for signatures that would be impossible for a classical horizon. Some theories predict a faint echo in the gravitational wave signal, a delayed repetition caused by partial reflection at a surface just outside the would-be horizon. Searches in the LIGO data have produced hints, but none that survive rigorous statistical scrutiny. The same applies to attempts to find a photon ring beyond the primary ring in EHT images, a narrow, bright feature that would arise from light looping multiple times around the black hole. Current resolution is insufficient. Future upgrades to the array may finally resolve it. Even the simplest measurements remind us of the limits of our instruments. The EHT's longest baselines give a resolution of about 20 microarcseconds at 1.3 wavelength. Enough to see the shadow, but not enough to map fine structure within the ring. Gravitational wave detectors are limited by quantum noise at high frequencies and by seismic noise at low frequencies. X-ray telescopes contend with pile-up and background flares that can obscure subtle line features. Each improvement in hardware opens a new window, yet each window still shows a grainy view of a much larger picture. In the end, the observational frontier is a patchwork of partial glimpses. The shadow tells us the spacetime is deep. The waveforms tell us the merger settles quickly. The iron line tells us matter can orbit just outside the horizon. Together they constrain exotic models, pushing their allowed parameters into ever narrower corners. Still, the data leave a quiet space where speculation can linger, waiting for the next photon or the next ripple to arrive. A single photon, recorded at 1.3 wavelength, traced the very edge of the bright ring and lingered for a fraction of a nanosecond before the detector registered its arrival. The equations that describe a black hole's edge feel like a sheet of cold metal, smooth at first glance, but with a subtle vibration you can't quite hear. When we push that sheet past the point where the light can no longer escape, we enter a region where the usual tick-tock of clocks stops. I keep asking myself what beyond even means when the flow of time itself seems to freeze. It feels like stepping into a room where the walls have no floor. There is space, but no direction for a step to follow. If time stops, does cause still have a hand? Determinism relies on a chain of events, each link pulled by the previous one. Inside the horizon, the chain seems to fray, the pull becomes uncertain. I find it hard to picture a cause and effect line that never meets a future. Perhaps the idea of a fixed future simply dissolves there, leaving a fog of possibilities that never solidify. That fog makes the notion of free will look both more fragile and more expansive, like a candle flame caught in a draft. Our brains are built to map cause to result, to feel the weight of a decision as a pressure on the chest. When we talk about a region where the metric of spacetime turns inside out, that pressure becomes a strange lightness. I sometimes stare at a simulation of an infalling observer and feel the same odd sensation as when I watch a marble roll off a table and disappear from sight. The marble is still there, but we cannot see it. Our perception defines reality by what we can register. When the register goes silent, reality may still be humming just out of earshot. One way to test these ideas is to look for subtle ripples that escape the horizon's grip. Gravitational wave detectors have already caught the faint sigh of colliding black holes, and each sigh tells us something about the interior's stiffness. The next generation of interferometers will listen for whispers that could hint at whether the interior behaves like a smooth continuation of spacetime, or like a chaotic tangle of quantum threads. If we catch a pattern that repeats, it might suggest that the interior respects some hidden order. If the pattern is erratic, it could mean that the laws we trust break down there. Quantum theory adds another layer of cold steel to the picture. The information paradox tells us that whatever falls in must leave a trace, yet the horizon seems to swallow everything whole. Some proposals suggest that the information is stored on a thin membrane at the edge, like a grain of sand that records every footstep. Others argue that the interior is a kind of holographic screen, projecting a three-dimensional scene onto a two-dimensional surface. Both ideas force us to rethink what real means when the usual dimensions lose their meaning. When I write down the equations, the symbols feel heavy, like lead, but the concepts they aim to capture are airy, like a thin mist. The mist can be traced, but only when the wind stops. In the case of a black hole, the wind is the relentless pull of gravity, and the mist is the quantum field that tries to spread. If the field can't escape, does it simply vanish, or does it linger in a form we cannot yet name? We don't really know. The answer may lie in a synthesis of general relativity's curvature and quantum mechanics' uncertainty, a synthesis that has eluded us for decades. Philosophically, the idea that a region of the universe could be cut off from any external influence challenges the very definition of existence. If no observer can ever receive a signal from inside, does that region belong to the same reality we share? Our senses have always been the gatekeepers of what we call real. When a phenomenon sits beyond the reach of any sense, we are forced to rely on inference, on the cold logic of mathematics. That shift feels like moving from a tactile workshop to a silent laboratory where only the hum of machines remains. The notion of free will also shifts under this light. If a particle crossing the horizon loses its ability to influence the outside, does it retain any agency? Perhaps agency is not a property of the particle, but of the network of interactions that can be observed. In that view, the interior becomes a silent choir, singing a song we cannot hear, while the exterior continues the chorus we can follow. The silence does not prove the absence of song. It only proves our ears are blocked. Future breakthroughs may come from two fronts. The first is theoretical, new frameworks that treat spacetime as emergent from deeper quantum entanglements. Some researchers are building models where the fabric of space is a lattice of entangled bits, each bit feeling a tiny tug from its neighbors. If the lattice tears at the horizon, the pattern of tugs could reveal whether the tear is a clean cut or a gradual fade. The second front is observational, instruments that can image the environment just outside the horizon with finer resolution, perhaps by capturing the polarization of light that grazes the edge. Each photon that escapes carries a faint imprint of the interior's geometry, like a fingerprint left on a glass surface. There is a quiet optimism in these efforts. The instruments we build are not grand monuments but precise tools, calibrated to feel the slightest tremor. The theories we write are not sweeping proclamations but careful conjectures, each line weighed against the data we have. In the lab, we watch a laser beam dance across a mirror, noting the tiniest jitter. That jitter may one day tell us whether the space inside a black hole is smooth or riddled with quantum foam. It feels modest, but the implication is large. Even if we never directly observe the inside, the act of probing it reshapes how we think about reality. We learn to accept that some questions may forever sit at the edge of what can be answered, like a mountain whose summit is always hidden by clouds. That acceptance does not mean we stop climbing. It means we learn to read the wind, the temperature, the way the clouds shift. In the same way, we may learn to read the subtle signatures that black holes leave on the universe around them. I sometimes wonder whether the beyond of a black hole is a doorway to something else, or simply the terminus of a path that ends in silence. The language we use, gateway, portal, boundary carries expectations of passage. Yet the physics suggests a different picture, a region where the usual coordinates dissolve, where the notion of direction loses its grip. It is less a doorway and more a place where the map stops being drawn. The human mind, for all its cleverness, is still a fragile instrument. It tries to fit the unknowable into familiar shapes to give a name to the nameless. When we speak of reality beyond the horizon, we are already stretching the word beyond its ordinary reach. That stretch feels uncomfortable, like pulling a rubber band until it thins. The tension is real, but the band does not snap. It simply becomes more translucent. In the coming years, I expect a steady accumulation of small clues, tiny deviations in waveforms, faint asymmetries in the glow of accretion disks, subtle shifts in the polarization of distant light. Each clue will be a grain of sand, and together they may form a pattern that hints at the interior's character. It will not be a single revelation, but a mosaic built piece by piece, each piece fitting imperfectly but adding to the whole. There is a certain humility in watching these pieces fall into place. The universe does not rush to answer our questions. It offers them slowly, like a cold river that reveals its depth only when you lower a stone. We drop our theoretical stones, watch the ripples, and try to infer the hidden current. Sometimes the ripples are too faint, sometimes they interfere with each other, but the river keeps flowing. As I sit at my desk, the glow of the monitor casting a pale light on the notes, I hear the faint whir of the cooling fans. It is a sound that reminds me of the low hum of a distant star, steady and indifferent. In that hum, I sense the same persistence that has kept scientists probing black holes for decades. It is not a dramatic drumbeat. It is a quiet, steady pulse. The final thought that lingers is the feeling of standing at the edge of a cliff, wind pressing against my face, not because I am about to jump, but because I am simply aware of the sheer drop. The cliff is the event horizon, the wind is the unknown, and the drop is the question of what lies when time ceases. I notice the cold metal of the railing beneath my fingers, a reminder that even in the abstract, we are still anchored to something solid.